Hello, I'm Pelin Ayser Baykal, and this poster is about inference and analysis of the global transmission network of SARS-CoV-2 prior to the pandemic declaration. The goal of this study here is to estimate the global transmission network of the COVID-19 before the pandemic declaration by World Health Organization on March 11, 2020. And secondly is to compare different transmission network reconstruction methods. On the right side, we explain our method. So first of all, our method is based on character-based phylogenetic tree. And we adopted this model because of the density of sampling and the amount of available data of SARS-CoV-2. And in our study, we specifically adopted the Kamin-Sokal phylogenetic tree model because SARS-CoV-2 violates 4-gamete rule, which creates repeated mutations, and we know that the Kamin-Sokal model allows homoplasy in the form of these repeated mutations. So first of all, we align our sequences to the reference sequence, and we form a mutation matrix M, in which the rows represents all sequences and the columns are representing genomic positions. And Mij will equal to 1 whenever it represents there's a minor allele with respect to the reference sequence. And here, if you take a look at the column 2 and 3, where the numbers are colored in red, you will see that they form all possible combinations of alleles, which are 0, 0, 0, 1, 1, 0, and 1, 1. And this is a representation of a 4-gamete rule violation, and which is the case for SARS-CoV-2 virus. So here's the first step of our method, is to identify potential repeated mutations. So for this, we use a graph whose vertices are SNPs, and those vertices are considered adjacent to each other whenever the corresponding pair of SNPs violates 4-gamete rule. And based on the mutation matrix here, we can see that 2 and 3, for example, violates the 4-gamete rule. And so there's a connection between 2 and 3, and if you look at 1 and 2, it's the same case, and there's a connection between 1 and 2. And after forming this graph, we generate minimum vertex covers, and here the sets of genomic positions corresponding to vertices in minimum vertex covers form the most parsimonious sets of repeated mutations. And to solve this problem, the minimum vertex cover problem, we use a Braun-Kerbosch algorithm. And the second step is to construct the mutation tree. So here, for each set of potential repeated mutations, we construct a character-based phylogenetic tree, T, which will maximize the likelihood to observe the mutation matrix M given T. And this is done using integer linear programming, which you can see equations on the right middle side. And then we select the most likely tree. So here on these equations, Xij equals to 1 whenever the genomic variant I has a mutation J from an extended set of P, and DJLAB equals to 1 whenever there's a sequence that have an allele combination AB at the position J and L. And the final step is to construct the transmission network, which is defined by the mutation tree T, and it's a D-graph whose vertices are viral genomes and their edges represents potential direct or indirect transmission linkage. And it is constructed as the transitive reduction of the reachability graph of the parents of the leaves of the tree T. And transmission trees are bootstrapped by the mutations subsampling, and the final transmission network is formed by their edges with sufficiently high bootstrap probabilities. So now let's look at the results on the left side. So our results show that the network highlights the different routes of SARS-CoV-2 introduction in different geographic regions, and it confirms the presence of multiple introduction paths for 14 out of 34 countries. And one of the characteristics of the transmission network generated by our model is that it's scale-free with a right-skewed degree distribution. And if you look at on the middle part, table shows that the Pareto distribution that represents the classical power law demonstrated the best fit to the observed degree distribution in our model. And finally, the final characteristic is that the network structure was found to be in line with the reported genome sampling times. And after we finished constructing our transmission network based on our model, we collected true transmission link information from different epidemiological publications, and we compare some benchmark tools with our model to see the performance of our model. And as you can see here, our model outperforms the other 4 benchmark tools with an 80% of sensitivity. Thank you for your attention.